If I just summarize where we were last time, at the end of the 1800s and the beginning of the 1900s, physics was in a position where it had a very, very good theory, universally accepted by scientists, for gravitation, associated with Isaac Newton. And we had an amazing theory associated with James Clerk Maxwell for electromagnetism. And at that moment in time, basically gravity and electricity were more or less, as far as we were aware, sorted. And I would just emphasize that the idea there was that the electromagnetic theory, according to Maxwell, it doesn't just explain about electricity, it doesn't just explain about Ohm's law, electrical power dissipation, I squared R. It also explains about all magnetic effects, magnetic field shapes, and it also explains about electromagnetism, the linking of those two types of field to produce what we call electromagnetic radiation. So it was a superb pinnacle of his work. It's just such a shame that Maxwell's name is not so well known, but in part that was because he died quite early, sadly. In the year 1900, at a talk, the photoelectric effect was one of the examples of a few small things that we hadn't quite sorted out. And at the end of the last session, we basically delved into what we meant by the photoelectric effect. The photoelectric effect is where we shine light, that's the reference to photo, onto a metal, and electrons come off the surface of the metal. We talked about the basic idea, light in, electrons out, and we explained that using the Maxwell wave model of light, which basically was waves have energy, the electrons get that energy, and they use it to escape from the atom. The idea of the electrons using that energy was also very simple. An electromagnetic wave has an electric field as part of it. That's the electro bit. And an electric field, like a gravitational field, influences charge. Gravitational fields influence mass. If I have a mass, like a lump of stuff, and I hold it in a gravitational field and let go of it, the object will be influenced by a gravitational field, i.e. it will fall. The strength of the gravitational field is what we call the gravitational field strength, and it is defined as the gravitational force per unit mass. In other words, the force of gravity on 1 kilogram. If we switch across to electric fields, the electric field strength is defined as the force per unit charge, the force on an object that has a charge of 1 coulomb in SI units. So imagine an electron in orbit around a nucleus, this image of the so-called solar system model of the atoms. The idea is that you have an electron whizzing around the nucleus, and then an electromagnetic wave comes along. Imagine that we've got a nucleus and we've got an electron in orbit, and the kind of idea is that, again, like the solar system model of the atom, it kind of like orbits around it, and then along comes an electromagnetic wave. Now we're only going to consider the electric part. The electromagnetic wave, sort of drawn a little bit like a wave like that, let's suppose it's moving towards the left, towards the atom. What happens is when we draw the wave like that, this is not a physical wave like sound is associated with a wave where we're kind of moving particles and oscillating particles. This is a field. So if I imagine that there's kind of an x-axis here, then it's interesting just to think for a second, what do we mean by the positive part of the wave compared to the negative part of the wave? And what we actually mean is the positive part of an electric field like this is going to create a force on a charged object, and the negative part will also create a force on a charged object, but in the opposite direction. When we have a positive and a negative field, so we have a positive field there, negative field there, when we flip the field, we're also flipping the forces on a charge. So what happens is as this electromagnetic wave moves past the heavy nucleus and the very, very light electron, it effectively pushes and pulls them. As the positive part goes past the electron, it pulls the electron. It doesn't really matter whether we say pulls or pushes. It's just the fact that when the negative goes past, it does the opposite. So as the electric field goes past, what happens is it pushes and pulls the electron in its orbit, and it gives it a little bit of energy. For every one cycle, if you like, that involves a push and a pull on the electron. So the electron starts to gain energy. And if the field is small, then that means that the push and the pull are going to be very weak. It's going to take a lot longer to get the electron to have enough energy with tiny pushes and pulls. Each cycle gives the electron a little bit of energy. If we had a very strong field like that, the red one, then the pushes and the pulls from that field are going to be much, much stronger. It's going to gain energy much quicker. Less cycles needed in order to give it enough energy to escape from the nucleus. So the idea was that when an electron is around a nucleus and an electric field, as part of an electromagnetic wave, goes past, it basically, for each cycle, gives a little bit of energy to the electron. And what happens to the electron? It gains a little bit of energy and starts to spiral outwards until it's gone far enough that it has enough energy and it's far enough away that it can then escape. That's the idea. So this is why, if we think about this, we have a few problems with the observations of the photoelectric effect. So let's get back to the observations that we discussed. We discussed 4 observations. 1, the photoelectric effect itself. Light goes in, electrons come off. That was quite easy, as we said before. Waves have energy, the electrons use the energy to escape. 2, if the intensity of the light increases, we see more electrons coming off. In other words, if you make the light brighter, we get more electrons. That was easy to explain as well. More intensity means more energy. More energy means you can use it to get out more electrons. Number 3, if the frequency of the light was below a certain specific value that depended on the specific metal. So lead, for example, would have a different value for this specific frequency than tin or iron or zinc. And this frequency was called the cutoff frequency, or sometimes called the threshold frequency. Then no electrons are observed. That was a problem. If we turn the frequency of the light down, we don't see, when it goes below a certain value, any electrons, no matter how bright we make the light, and no one could explain that. The problem was that the electrons seemed to be completely ignoring the energy of the electromagnetic wave, and no one could understand why. What was happening to the pushes and the pulls? Why weren't they working? And then number 4, almost no time delay. So this is really a reference to what we've just been talking about. If you make the intensity of the electromagnetic radiation very weak, in the wave model, that means a very small amplitude. Then the pushing and the pulling, as you try to give the electrons more and more energy, is smaller and smaller and smaller. And that means it's going to take much longer to get the electrons to have enough energy to escape. And we didn't see that. Basically, the time it took to turn the light on, no matter what the intensity, was basically instantaneously, as far as we could ever measure, and no one could explain that. This was done in 1887, 1888 by Hertz. By the year 1900, this still had not been explained. Physicists thought it would be, we just hadn't quite hit upon it. And then up pops Einstein. Einstein explained the photoelectric effect with what he called the particle model. Einstein gave us a beautiful explanation of E with his particle model. Now, imagine that we have a torch, and imagine that that torch gives out a beam of light, and I know that torches don't normally give out a beautiful beam of light. Okay, the wave model is the idea that the torch will be giving out light in the form of lots and lots and lots of waves. So this is a sort of a graphical image of what the wave model was doing to describe light. And of course, each one of these ridiculous numbers of waves, they all travel at the speed of light. The particle model was the new model. The particle model described an electromagnetic beam as a collection of particles, little lumps of electromagnetic energy, all traveling at the speed of light, of course, and these were called photons. And the energy of a photon was given according to Einstein by an equation: energy equals hf. H or Planck's constant, and it equals 6.63 times 10 to the minus 34. Units are joule seconds. And F, as you might imagine, is the frequency. And Einstein said, this is what a light is. Light is not a collection of waves. It is a collection of tiny lumps of electromagnetic energy called photons. And the way that Einstein explained the photoelectric effect was in the following. Number one, light produces electrons. The electrons absorb photon in a one-on-one collision. Now, this is really important, and I don't think the textbooks emphasize this enough. I don't believe that this can be overemphasized. Electrons absorb one photon. They do not hang around grabbing photons till they have enough energy to escape. They grab one photon, which happens to collide by random fluke, by random statistics, by random probability. One of those photons happens to hit the electron, and the electron absorbs it, and it must use the energy straight away. Now, electrons are fundamental. In physics, the word fundamental, with reference to particles, means that it has no internal structure. It is the idea that the ancient Greeks had about being indivisible. The ancient Greeks had this idea that if you take a lump of stuff and you chop it and you chop it and you chop it and you chop it, you'll get a half, and then you chop it, you get a quarter and a 16th and a 32th and a 64th, etc., etc. And if you keep going, you will eventually end up with something that was indivisible. And that the ancient Greek word for indivisible was atomos, and that's where we get this idea of the atom. However, nowadays we know that atoms actually are, you could argue, the basic building blocks of everything around us, but actually they're not indivisible. They're made of smaller particles. Well, turns out that an electron is indivisible. An electron is what the Greeks were referring to when they said you can't divide it. An electron cannot be split. It has no internal structure, which means it has no mechanism for absorbing and hanging onto the energy. When it absorbs the photon, it has to use the energy instantly. It cannot hang on to it for a bit, wait for another one, and then use both of them together to escape. That cannot happen. It is a one-on-one interaction. So the electrons absorb a photon in a one-on-one collision. The energy is then used to escape the atom. So that was his argument for point one. Point two, if I increases, I'm going to use my up arrow for increases. There are more photons in a given length of the beam. Therefore, more electrons can be emitted, because basically the maximum amount of electrons that you're going to get out is if it's kind of like one-on-one and all those photons just get absorbed. In reality, of course, all the photons won't get absorbed. But the idea is if you've got more photons there, there's more electrons that can absorb them and you'll get more electrons out. Okay, number three, the cutoff frequency. If F is less than the cutoff frequency, the photon energy, which remember is equal to hf, is not big enough to allow the electron to escape. This is why, if the frequency of the light is below a certain value, you don't see any electrons. It's not that it's something crazy going on where the electrons aren't there. It's just that the photons don't have enough energy to give to the electrons, so that they can leap away from the nucleus, which of course they're attracted to, and escape. And then number 4, the time delay. The time delay is simply time for the photons to reach the surface, be absorbed, and the electrons escape. And it doesn't matter whether the intensity of the electromagnetic radiation is low or high, it's the same time. If you remember, in the wave model, a low intensity meant a very low amplitude for the wave, so it would take a lot of pushes and pulls. The pushes and pull idea now is a complete irrelevance. That's not the way this works. If the intensity is very low, it just means you don't have many photons, which means you don't get many electrons. But it's still the same amount of time to get the photons there, because they're traveling at the speed of light, to get absorbed, which will take a very short period of time, and then from them to leap out. So we have the so-called particle model of light. And the particle model of light associated with Einstein was like a crazy success. Everybody was really happy. Einstein's particle model was a huge success and seemed to show that wave model was wrong. So what they did was they looked at all those wave effects. Sadly, Einstein's particle model completely failed in explaining so-called wave effects. It could not explain diffraction patterns, interference, refraction. So this was a real problem, because people thought when Einstein explained the photoelectric effect that we now finally understood what the heck light was. We'd moved from Maxwell's wave model to Einstein's particle model. And we'd moved that way because the wave model had failed. Unfortunately, the success of the particle model didn't last very long. As soon as they applied it to these wave effects, it failed as well. It left us with 2 models for light. So we now have 2 models for light. And we have a name for that particular problem. It's called wave-particle duality. And wave-particle duality is a bit of a pain, because it means that we don't really fully understand what light is. It's not a wave, it's not a collection of particles, it's something slightly different. We're not quite sure what it is. And we are effectively still left with this idea now. We have the wave model and we have the particle model. And the wave model is obviously for things like reflection, refraction, interference, and diffraction. And the particle model is used for things like photoelectric effect, or the Compton effect, and absorption and emission spectra. And we have to make sure that when we do anything where we're analysing light and what it does, we use the right model. If we are looking at a particular situation, let's say we're looking at emission spectra from a star, in order to explain what we see, we must use the particle model. It doesn't mean we can't use the wave model, but if we do, we will not be able to explain the fine detail of what we observe. This is the point. The right model for the right effect, which feels, again, really irritatingly annoying. The story now moves forward. We now need to talk about something called matter waves. Now, there was a French physicist named de Broglie, although the British, being pretty awful at languages, would probably say de Broglie. De Broglie was studying for his PhD in physics. The criteria is that you have to add to the sum total knowledge of mankind. In other words, as a result of your work, which normally is a 3-year piece of research, mankind should know more about the universe as a result of your work than it did before you did your work. That's the criteria. And de Broglie was studying for his PhD in physics and made the following statement. First of all, he said, light shows wave-particle duality. Now, that wasn't new. That was a result of the knock-on effect from Einstein's work on explaining the photoelectric effect. His contribution was the next bit. Also, matter shows wave-particle duality. Matter is stuff with mass. Mass shows wave-particle duality. So mass behaves as if it has a particle nature and also a wave nature. Now, this is a really weird statement. A lump of mass, like a pen. I hold up a pen in my hand. It doesn't look like a wave to me, it looks like a particle. No one believed him when he made this statement. Turns out that he was actually related to the French aristocracy, and he was a French prince. So even though his work was really received very skeptically, and basically a lot of people thought it was rubbish, he still was given his PhD because, well, he was a French prince. What are you going to do? But I hold a pen in my hand. It doesn't feel like it has any kind of wave nature. It definitely feels like a lump of stuff, a particle. If I throw it, it moves like a particle. It certainly does not, if I throw it through a doorway, spread out like a wave would because of diffraction. So this seems to be ridiculous. However, he was at pains to point out he didn't mean that the matter, the mass, the lump of stuff actually is a wave. It has a wave nature. So let's just finish this session by just stating in a little bit more detail what he was making as the basis of his PhD. Matter can be described as having a wave nature. The wave that we write down is called wave function. The square of the wave function is proportional to the probability of finding the particle. And he also gave us a way of finding out the value of the wavelength of this wave function. Wavelength given by lambda is h over p, where p is momentum. So this is Planck's constant over mv. We'll bullet point those, and next time we'll look at the implications of these statements. We'll talk about what these wave functions might look like, and then we'll try to bring some maths into a description of it.